So Coulomb's law describes the electric force due to the interaction between charges. But to set this up, we're going to go back and talk about the universal law of gravitation, which described the interaction, the gravitational attraction between particles due to mass. So what the universal law of gravitation tells us is that the gravitational force between two particles with a mass of m1 and m2 that are separated by a distance r has the following properties. One, it's directed along the line joining the two particles. Two, it is attractive, so it's an attractive force. Three, you calculate its magnitude by taking big G times the product of the masses divided by the distance between them squared. And big G is what's known as the universal gravitational constant, and it has a value of 6.67 times 10 to the negative 11 in SI units. So Newton meter squared per kilogram squared is one way to write the units of big G. All right, so this was the universal law of gravitation describing the interaction between masses. Coulomb's law describes the interaction between charges. And so what Coulomb's law tells us is that an electric force between two particles with charge Q1 and Q2 separated by a distance r has the following properties. One, it's directed along the line joining the two particles. Two, it can be either attractive or repulsive. So you all have known for many years now through your schooling that like charges repel and opposite charges attract. And part of what this means is the reason we need two types of charge that we choose to label positive and negative is because we have to explain two types of behavior with the electric force. Mass is always attractive gravitationally. The gravitational force always pulls mass together, so you only need one type of mass. We don't have to worry about positive or negative. But the electric force can both attract and repel depending on whether your charges are the same or different. So we need two types of charge. We choose to label those positive and negative. So in our sort of picture on the left, we have opposite charges denoted by one being red, the other being blue. They're attracted. We have two of the same types of charges on the picture on the right, both red, they're repelled. Three, the magnitude of the electric force is given by Ke times the product of the two charges, and again, because they can be positive or negative, we're just going to go ahead and put both those in absolute values to make sure that we end up with a positive quantity when we multiply them together. And then that's divided by the distance between the particles squared. Ke is known as the Coulomb's constant, and it has a value of 8.99 times 10 to the 9th. And again, in SI units, one choice we have is to use units of Newton's meter squared per Coulomb squared. Okay? So there's a lot of similarity between the universal law of gravitation and Coulomb's law. So what's this equation telling us? So here's the equation for the magnitude of the electrical force between two charges. So K Q1 Q2 over R12 squared. And so in terms of what does this equation tell us? Well, the first thing it says is that the electric force is proportional to the product of the two charges. Well, this indicates a couple of things. The first is we know that all forces are interactions between two objects. The electric force is clearly an interaction between two charged particles. So Q1 and Q2 is making it clear that we have two charged particles. That's what's doing the interaction that generates an electric force. Objects feel an electric force because they are charged and in the presence of another charge. So it takes two charges to generate an electric force. What else does this equation tell us? Well, again, the electric force is proportional to 1 over the distance between your charges squared. So R12 is just saying the distance between particle 1 and particle 2. That distance gets squared, which means the larger the distance between the two objects, the weaker the magnitude of the electric force between them. If you double the distance between your 2-point charges, the electric force is going to fall off by a factor of 1/4, right? This is known as an inverse square law, just like the gravitational force between masses. So the universal law of gravitation was also an inverse square law. What else does it tell us? Well, because the electric force is proportional to the product of charges divided by the distance squared, the Coulomb's constant is that constant of proportionality. Now, there are a couple things to point out here. One is that, again, it serves the same function in terms of thinking about its units as big G. We used big G because we wanted, in our universal law of gravitation, because we wanted to end up with a force, units of newtons, and we took a masses squared over distance squared, and so we needed something with this units to cancel out the product of masses over a distance squared and leave us something with force. In terms of thinking about units, again, one reason why we can write the units this way for the Coulomb's constant is, again, its function is to convert a product of charges divided by a distance squared into a force. So again, I want to be left with newtons, units of force, and I need to cancel out distance squared on bottom, so there's meters squared on top. I need to cancel out my product of charges, Coulomb squared on top, there's Coulomb squared on bottom. So sure enough, this unit that we're choosing to use here is, again, just emphasizing that my constant of proportionality is just converting something that has units of Coulomb squared over meter squared into something that has units of force. Now, the other thing to notice, of course, is that big G is some number times 10 to the negative 11th. Ke is some number times 10 to the 9, which means that the Coulomb's constant is, roughly speaking, 10 to the power of 20 times larger than the universal gravitational constant. This means that you can have significant electrical forces even if you don't have very large amounts of charge. In fact, almost any problem we're going to work with is not going to have much charge. We're going to use units this semester when we're dealing with charge, where we'll often use charges in units of millicoulombs, microcoulombs, nanocoulombs, maybe even picocoulombs, right? So we're going to be using very small amounts of charge, but that's still going to give us the possibility of having some reasonably large forces, simply because that Coulomb's constant is as big as it is. Now, the other thing we'll highlight here is that the Coulomb's constant is actually related to what we tend to think of as a more fundamental constant that shows up in a lot of these problems with electricity. So epsilon naught is known as the permittivity of free space. And again, the Coulomb's constant is equal to 1 over 4 pi times epsilon naught. So we could, and sometimes you will see this, where the magnitude of the electric force is written as the product of our charges, so again Q1 over Q2, divided by 4 pi epsilon naught times the distance squared. That's going to give you the same thing, because instead of using K out front, you're using 1 over 4 pi epsilon naught, which is what K is equal to. The permittivity of free space, again, if K is a very large number, the permittivity of free space has to be a really small one, since one of them's basically in the numerator, the other one's in the denominator, and so it happens to have a value of 8.85 times 10 to the negative 12. There it's SI units, Coulomb squared over Newton per meter squared. And again, just to sort of preview, we'll see epsilon naught a lot over this semester. It is a fundamental constant for the universe in the same way big G is a fundamental constant for the universe. All right, so what else is Coulomb's law trying to tell us? Well, notice that we have not just a magnitude but also a direction, because of course all forces are vectors, which means the electric forces, those are also vectors. And so we end up in a situation where we can have multiple forces because both charges feel a force, right? So notice that, just again using the labeling that we've used in the first semester of the course, Fe1,2 says the electric force on charge 1 by charge 2. Well, that's the force describing how charge 1 is in this case attracted to charge 2. Newton's third law says that there's going to be a Newton's third law pair to that. It's going to be the same type of force. We're going to switch which charge causes it and which charge feels it. And so we have the electric force on charge 2 by charge 1. Those two forces are equal in magnitude, magnitude given right here by our expression. They point in opposite directions because, again, they're both vectors, and direction matters. So one of the things to make clear is, so here we have two forces, one points to the right, the other one points to the left. And so the sign that we end up using, again, when we write out the components for these vectors, is due to our choice of coordinate system. So just like in all of our vector problems, the sign is really determined by which direction you pick to be the positive direction. So in this example, let's say we've picked positive x pointing to the right. Well, that means the force on charge 1 by charge 2, that points to the right, it's going to be positive. The force on charge 2 by charge 1, where charge 2 is pulled back to the left, that needs a negative out in front. The important detail is, again, these absolute value signs. The sign does not come from the signs of your charge, right? We're just using this expression, the kqq over r squared, to get the magnitude, and then the sign is really up to us because it depends on what we've done with our coordinate system. So what do we do when we have multiple charges? Well, again, if these are vectors, then what we need to do if we want to figure out the electric force on, in this case, charge 1 due to charges 2 and 3, there's going to be two interactions here, one between charge 1 and charge 2, the other between charge 1 and charge 3. So I'm going to have two force vectors, and so I need to add them up as force vectors. So when we're calculating the net electric force on a charge in the presence of multiple other charges, we're just going to be working a vector summation problem. So electric force vectors, we're going to sum them as vectors to get the net electric force.